So let me begin by presenting the problem we aim to solve. In discrete mathematics, understanding reflexive, symmetry and transitive relation is a fundamental concept. However, many students struggle when it's come to actually determining whether a given relation satisfies these properties, especially when dealing with large sets containing dozens or even hundreds of elements. So manually checking each order pair is not only tedious and repetitive, but it also opens the door to human error. Missing just one pair can lead to an incorrect conclusion about the entire relation. So the challenge becomes even greater when we need to generate closure. For example, finding the transitive closure requires repeatedly checking for missing pairs and adding them, which become increasingly complex as the relation grew. So this process can take several times, and it's very easy to get wrong when done by hand. So to solve this, we develop a program that automatically verifies these properties and generate the necessary closure to our system to eliminate the manual error, save time and ensure consistent accurate result. Now let's me provide some background on why this topic is matter. So relation are core concept in discrete mathematics. In simple terms, a relation is a set of ordered pair that show how elements from two sets are connected. For example, in computer science, relation appear in database system, network graph and algorithm design. So this is the three key properties we should focus on, which is the first one is a relation is reflexive if every element is related to itself, meaning AA exists for all elements. Second one, it is symmetric if for every pair AB, the reverse BA is also present. The third one, it is transitive if whenever AB and BC exist, then AC must also be included. When all three properties are satisfied, we call it an equivalence relation, which is very useful for grouping elements into meaningful categories. However, manually checking these properties can be time consuming and error prone, particularly with complex data sets. That's why our project focuses on building a tool that automates this entire process from verifying properties to generating reflexive, symmetric and transitive closure. Not only this, we also improve accuracy and efficiency, but it also serves as a valuable learning resource for students to better understand binary relation through the hand-on practice. With that, I covered the introduction and the problem of our project address. So our program provides a practical automated solution to this challenge, making it easier for students and professionals alike to work with relation effectively.
Assalamualaikum to our lecturer, Madam Zulaika, and my fellow friends. My name is Putri Nursyazwani Binti Muhammad Amrun, and I will be presenting about algorithm and pseudocode of our system. To ensure our program evaluates the properties of relation accurately, we designed a structured logical workflow. Let me walk you through how the algorithm processes the data from the start to finish. First, the program starts by requesting the user to input the total number of elements they wish to evaluate in the relation set. Once this value is read, the system initializes two primary data structures, a vector array named R to store the incoming ordered pairs, and a mathematical set named A, capital letters A, to track all unique elements participating in the domain. A loop then executes to read each pair. As the user enters values for element A and element B, the program dynamically inserts them into capital letter of A. This ensures that if the user types elements like 1, 2, 3, or 4, our system knows exactly that the universal elements are without hard-coding them. Next, the system moves into the core processing phase, which handles the validation logic for all three target properties. First, the reflexive check. The program loops through every unique element X inside our set capital letter of A. It searches the relation vector to verify if the identity pair XX exists. If any identity pair is missing, the reflexive flag drops to false and that the specific missing pair is pushed into a temporary array so we can build the closure later. Second, the symmetric check. The algorithm scans the relation array. For every ordered pair A, B discovered, it search for its exact structural inverse, B, A. If the inverse is missing, the relation is flagged as non-symmetric, and the missing pair is captured while automatically filtering out duplicates. Third, the transitive check. The program uses nested loops to trace cross-chain connections. If it finds a pair AB and another pair BC where the second element matches the first element of the next pair, it immediately looks for the direct link AC. If AC does not exist, transitivity fails and the missing path is recorded. Finally, the system outputs the structural property summary telling the user whether the relation is reflexive, symmetric, and transitive. It then prints the computed reflexive, symmetric, and transitive closures by outputting the original relation R united with the respective missing pair arrays. This robust workflow allows our program to process any user-defined relation dynamically and accurately. Thank you, and I will now pass the presentation to the next member.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nursyarika binti Ahmad and I will explain about the coding. So, I use Python with the tkinter library for the GUI. The most important part of this code is how it handles the mathematical logic for relations, which I have separated into clean modular functions. So first, let's look at how the program reads the input. For the set A, I simply split the string by commas and convert it into a Python set. For the relation R, I use regular expressions to extract the numbers inside the parentheses, convert them to integers, and store them as a set of tuples. Using Python's built-in set data structure is very efficient because it allows me to easily check if a pair exists in the relation later on. Now let's look at the property checking function. So for reflexivity, the rule is that every element A in set A must have A in the relation. I use simple for loop to iterate through set A. If it finds even one element where A is missing from the relation, it immediately returns false. If the loop finishes without issues, it returns true. So for symmetry, the rule is if A, B is in R, then B, A must also be in R. I iterate through every pair in the relation. For each A, B, I check if the reverse tuple B, A exists in the set. If it's missing, it returns false. For transitivity, this is slightly more complex. The rule is if A, B, and B, C exist, then A, C must exist. So I use nested loops to check every possible combination of two pairs in the relation. If the second element of the first pair match the first element of the second pair AC is in the relation. If not, it returns false. Now let's look at part D, generating the closures. So for reflexive and symmetric closure, these two are straightforward. For reflexive closure, I just take the original relation and add AA for every element in set A. Meanwhile, for symmetric closure, I iterate through the relation and add BA for every AB that exists. So for transitive closure, I implemented an iterative approach. I use a while loop that keeps running as long as new pairs are being added. inside the loop, it checks all pairs. If it finds AB and BC, it adds AC to a new pair set. After checking everything, it updates the main closure with these new pairs. The loop only stops when a full pass is met and no new pairs are added, meaning the closure is complete. Finally, all these mathematical functions are connected to the GUI using tkinter. When the user clicks check properties or generate closure, it triggers these functions, format the output into a readable strings, and display it in the scroll text widget. I also added basic error handling using try except blocks to prevent the app from crashing if the user types invalid input. So this is the interface and also the sample of the output. That concludes the code walkthrough. The logic is fully implemented according to the discrete mathematics rules for relations. Thank you.
Hi, my name is Jamila Khayrin Binti Aziz, and I will be representing our analysis of result. For our testing phase, we use a sample set A containing the element 1, 2, 3, 4 with a specific relation R. Through this setup, the system successfully verified three key properties. First, it verified the reflexive property. The system checks if every element has an AA pair, for instance, having pair like 1, 1 and 2, 2. Second is the symmetric property. This means every AB pair must have an inverse BA. As you can see from our example, the present of 1, 2 matches with 2, 1. Third, it verified the transitive property where chain relation hold true. For example, the combination of 1, 2 and 2, 1 correctly maps to 1, 1. As a final output, the system concludes that this specific relation is reflexive, symmetric, and transitive, which essentially means it qualifies as an equivalent relation. That concludes this section. Thank you. To conclude, our closure result shows that zero external pairs were added. This is because the input relation already satisfied all mathematical rules from the start. As for our key takeaways, this project successfully bridged abstract CSC510 theory with practical Python programming. Throughout the process, we learned how to master GUI layout, regex parsing, and looping algorithms. In the real world, this kind of transitive logic is highly useful for optimizing network routing and logistic systems. That's all from us. Thank you.